Hello, everyone, and welcome to Chapter 8. Rolling right along to mixtures, solution concentrations, osmosis, and dialysis. This is the longest chapter title. It's got 6 sections, so it looks like a lot, and it kind of is, but I think we're going to try to get through 1 and 2 as quick as we can. It's important, but we're going to spend the majority of our time on 3, 4, and 5. So we're going to spend a lot of time talking about concentrations and uh, calculations. Yes, calculations. But they're related to medicine and dosage and things like that. So this is going to be, I think, one of the most important chapters for you. So let's get started on types of mixtures and what a mixture is. So here's a nice chart of chemistry, of matter, right? Chemistry is the study of matter and changes in matter. And everything we've done up until now has been over here, right? We talked about substances. I kind of walked you through this um, too, like how they built upon each other, right? We had substances, and then we had elements, and then elements add together into compounds, and there's ionic and covalent compounds, and then we extended it to talk about um, structure and molecular shape and intermolecular forces and polarity and all those kinds of things. By the way, monatomic and diatomic would be a diatomic is like H2, O2, N2, and so on, where the element comes as a molecule of two. Monatomic are the typical or normal, like most, you think like calcium, uh, silver, lead, stuff like that. Okay, so this chapter then is the other branch, which is not pure substances, mixtures. And we talked about this briefly with gases. We talked about gas mixtures, and we can define a mixture simply as a combination of two or more elements and or compounds in any proportion. So it's very broad, right? It can contain elements or compounds, or one of each, or multiple of each in any proportion. Doesn't matter. It's just all stuff all mixed together. An important thing about a mixture is that it can be separated back out, usually by physical separation techniques. um, and so some examples. So we'll go in more detail in here in a moment. But some examples of mixtures. A not very interesting one, but I don't know why he would do this. We get a mixture of sand and sugar, right? So they're two separate things. They are compounds separately, and here they're just mixed up. Blood is a mixture of many components. Obviously, there's a lot going on inside there, and they're not like reacting with each other. They're just all mixed in together. The gasoline that you get at the pump, if you're still doing that nowadays, it's very cheap, um, is a mixture of different hydrocarbons, right? That's why they have different like octane ratings, different prices. Some mixtures are premium, regular, and so on. And then from last chapter, right, mixture of gases. So these are all just just simple examples of what a mixture could be. It could be solid, could be liquids, could be gases, and it could be a combination of solids and liquids. But the important thing is it's a mixture. It's a mixture is a physical phenomenon, not chemical. Okay, but it's still really important in chemistry. Now we can break this down again. If we go back to our chart. A mixture can be broken down into two types, homogeneous and heterogeneous. So a homogeneous mixture is basically evenly distributed throughout the whole mixture, whatever the components are. This example here would be a cup of coffee. Um, or another one could be the air in a room, right? And so the idea of a homogeneous mixture is that if you were to take a sample from any part of this mixture, you would get the same distribution of parts, right? So a cup of coffee, if it's stirred, it doesn't have creamer or whatever, um, if you stick your spoon in the top or you stick your spoon in the bottom or in the middle or anywhere, it would be evenly distributed, and you'd get the same sample everywhere, right? In contrast to that, a heterogeneous mixture is unevenly distributed throughout the mixture. So here's an example of, I think, a piece of granite. And even just looking at it, you can clearly see that there are different sections, right? Like if you were to take a chunk off of this corner and a chunk off of this corner, they would not have the same distribution of parts. So one way I like to think about this is like imagine you just have a big vat of this mixture, some giant sample. And think if you were to take a sample of it or extract a piece of it from two, different parts all the way out at the edges from each other, would you get the same thing? Now there's a further distinction, and there can be two types of homogeneous mixtures, and that would be solutions and colloidal dispersions. These mixtures differ in the size of the minor component or the size of the parts, right? So we see this branch. Homogeneous can extend to two types, but heterogeneous only has one more leg beyond it. So a suspension is a heterogeneous mixture. Heterogeneous are more descriptive, and this third row are just more the names, right? So the smallest particles, or the minor component of the mixture, the one that there's less of, are called solutions. So if the components are less than a nanometer, it's called a solution, and the smallest particles, or sorry, the minor component, the one there's less of, is called the solute. And this would be just a transparent solution, right? You wouldn't be able to see the particles, they're so small. A colloidal dispersion contains particles in the intermediate size. So something from like 1 nanometer to 1 micrometer, um, which is still an order of 1,000 times bigger. A micrometer is 1,000 times bigger than a nanometer, so it's still a pretty big range. A nanometer, remember, is 10 to the minus 9 meters. So colloids are still kind of visible. They make for a cloudy um, appearance, but you can't see the individual particles, but you can see the effect that light has when it passes past them. And a suspension contains large particles and is usually cloudy, and also you can see visible particles, right? So classic example that I think that I give for suspensions would be like Italian salad dressing. Okay, Italian dressing has chunks of various herbs and spices and things in it, and you can clearly see the chunks. And another defining feature of a suspension is that you might have to shake it because it settles. So the particles would settle. Like if you take the dressing out of the fridge, all the big chunks are in the bottom, right? And so it's you'd want to shake it and mix it up. And even upon mixing, though, it's still heterogeneous because um, not the top of the bottle and the bottom aren't going to be identical to each other. Um, so that's one way to kind of think about suspensions is if you can see the individual particles and if the particles would settle, then it's suspension. Um, but aside from that, like pretty much all we're going to talk about are solutions because we're going to talk about elements and compounds which are generally small. and so they're going to be solutes. So let's stop here with part one, and then we'll talk more specifically about solutions and the parts of a solution next.